Good afternoon, class. We are looking at Chapter 2 review, limits and derivatives. Exam 1 review, we're going to cover from 2.4 to 2.6 now, the precise definition, continuity, limits at infinity, horizontal asymptotes, HA for short. So here's the precise definition. The limit of f of x as x approaches 3 equals 5 means f of x is close to 5 when x is close to 3. So here's x along the x-axis, and you have 3 minus delta on the right, 3 plus delta on the right. So that means you're approaching 3 from the left here, approaching it from the right here, and delta is a very small number. The result is 5. And again, you're approaching 5 from the bottom, 5 minus epsilon from the top, 5 plus epsilon. Delta and epsilon are both small positive numbers. So the synopsis of that, and we're going to go over that in a moment, reads, whatever epsilon larger than 0, there exists a delta larger than 0, such that if the absolute value of x minus a, which refers to the distance, is less than delta, then absolute value of f of x minus L is less than epsilon. By the way, this reads, just for the sake of argument, this reads in mathematical symbols, whatever. This means there exists, and this is a line segment that reads such that. Okay, so just in case reading the symbol. So one more time, whatever epsilon larger than 0, there exists delta larger than 0, such that if absolute value of x minus a is less than delta, that results in absolute value of f of x minus L is less than. So now that's exactly what we are saying here about the difference is mathematical symbols. So now we can make the values of f of x within an arbitrary distance epsilon from 5 by restricting the values of x to be within a distance delta from 3, but x cannot be equal to 3. That's the concept of a limit. We never reach 3, but we are moving towards that. Therefore, x is between 3 minus delta and 3 plus delta. That's by definition of an absolute value, reminding you, everybody, when we have absolute value of x less than k, if k is positive, x is sandwiched between minus k and k. That's the meaning of it, right? Then 5 minus epsilon less than f of x less than 5 plus epsilon. Again, same definition. If k is a positive value, absolute value of x less than k means it's sandwiched between the two. By taking the values of x, in this case, not equal to 3, to lie in the interval of 3 minus delta and 3 plus delta, we can make the values of f of x, meaning the y coordinate, lie in the interval of 5 minus epsilon, 5 plus epsilon. Let me erase my word. Precise definition of limits. Let f of x be a function defined on some open interval, or the open interval that contains a except possibly at a itself. We say the function has a limit at a, the limit of f of x as x approaches a is L, if for every small number, epsilon larger than 0, it's a very small number, there's a number delta larger than 0, it's a very small number, both of them again, such that if the absolute value of x minus a is between 0 and delta, then absolute value of f of x minus L is less than epsilon. In other words, you can think of the concept in this manner. We are moving towards a from the left and right. The distance is delta maximum, if you will, and that maps the x coordinate to the y coordinate, or f of x, if you will, within the limit of L, again, by plus minus epsilon. So L minus epsilon, L plus epsilon, and of course, that's along the y-axis. So that's the synopsis of that. Example 10, use the graph to find delta such that if absolute value of x minus 3 is between 0 and delta, absolute value of f of x minus 2 is less than 0.5. Now, a couple of things I want to mention. Again, I'm reminding you that if we have something like that, that means x minus a, as long as b is positive, is sandwiched between negative b and b. That's the meaning of it, okay, that we are going to use here. And this is the definition that we used in the previous page. So what it means, guessing a value for delta, given epsilon larger than 0, we need to find or guess, if you will, delta larger than 0 such that if absolute value of x minus a is between 0 and delta, then absolute value of f of x minus l is less than epsilon. And if you look at the graph, just the graph, although there's a process I'm going to show you, the idea is that number 3 is here, and just a little bit to the left, just a little bit to the right, that is acceptable. It results in the limit to be 2, again, a little bit down, a little bit up by, as it appears, 0.5. Okay, so in this case, if we start, and we always start with this part, the limit of the absolute value of f of x minus l is less than epsilon. If you want to go with numbers here more specifically, so the absolute value of f of x minus l, in this case, the limit is 2, okay? Less than epsilon in this case is 0.5. And by the way, when you have an epsilon or delta, any value that you have, smaller values work. So epsilon has been chosen to be 0.5. We want to see what should um, delta be. That's the concept. Now, of course, as far as the absolute value is concerned, following that, we can drop the absolute value, sandwich it between negative and positive 0.5. Then we add 2 to all sides. In other words, plus 2, plus 2, plus 2 everywhere. And that means, of course, f of x is between 1.5 to 2.5. We already can see that from the graph. But just in case it's not given as far as the graph, this is how you come up with that. Now, what about delta? You should always, and it's given again, if you look at the graph, you should always look at the distance and pick the smaller of the two. X is between 2.6 and 3.8, according to the graph. So we have this distance, 3 minus 2.6, and this distance, 3.8 minus 3. This is 0.4, this is 0.8. So this distance versus this distance. Obviously, this is smaller. You should always pick the smaller of the two. So the minimum value of these 2.4 and 0.8 is 0.4. Now, of course, any smaller number than 0.4 will do the job. And as always, x can't be equal to a. In this case, x is not equal to 3. I want to make sure we understand why we pick the smaller of the two. When you pick 0.4, the smaller of the two, you go 0.4 to the left from 3. You end up here. You go 0.4 to the right, you end up somewhere here. However, if you choose 0.8, as you go from 3 to 3.8, you end up here and it's not a problem. But if you go 0.8 to the left, meaning if we go here, and this distance is 0.8, then this number will be somewhere here, which is outside the range of 1.5 to 2.5. You must always pick the smaller of these two, and any number less than the smaller one will always work. Now, prove that the limit of 4x minus 5 as x approaches 3 equals 7. This is the precise definition. Remember, we basically plug in 4 times 3 minus 5 equals 7. And if it works out, it works out. But as far as the precise definition, just to give you an idea, I like to go with this format that I have. And write this as absolute value of x minus a, which is 3 less than delta. Therefore, f of x, which is 4x minus 5. So I replace the f of x with 4x minus 5 minus L, which is 7 less than epsilon. So I start with that. Now, this is the write out. So just follow this, replace the A, replace the f of x, replace the L. This is the way the proof works. Then you always start with 4x minus 5 minus 7, the second part less than epsilon. This is how the proof works, as you recall in algebra. So let's work it out. The idea is that from here, you get to an expression that contains this, and you find the relationship between epsilon and delta. So let's write it in this fashion. 4x minus 5 minus 7 is 4x minus 12 or less than epsilon. I can take the 4 out, and I can take the 4 outside the absolute value. Now, if I divide both sides by 4, I get absolute value of x minus 3 less than epsilon over 4. Now it looks almost like that. If I put this next to it, we notice, compare it to absolute value of x minus a less than delta, we notice the left side, they are identical. So what would be, or what should be the choice of delta? Delta should be epsilon over 4 for this to work. That's the idea. So a quick recap. You start with the second part, which is this one. You work it out such that you get the first part, and then that gives you a relationship between sigma, epsilon and delta. And now, of course, a quick reverse process to show that this works. You start with this part, and you write both of them. Sigma equals epsilon over 4. Clearly, we're going to multiply both sides by 4. So 4 times that is 4 sigma or epsilon. We can put the 4 inside. Remember, it's the reverse process. We are going back. And I can take the 4x minus 12 inside, because 4 times x, 4 minus 12 is 4x minus 12. I can take this inside and say 4x minus 5 minus 7, because I want to make sure it will look like this. See, I'm going this way. And that, from here to here, indicates that we got the entire thing here, or this one, if you will. So if x minus 3 is less than delta, absolute value of 4x minus 5 minus 7 is less than epsilon. That's the original one that we have. And that shows the limit of 4x minus 5 as x approaches 3 is 7. So if we look at the graph, in the vicinity of 3, to the left by delta, to the right by delta, 3 minus delta, to the right 3 plus delta, we get in the vicinity of 7, the functional value, the y coordinate, the limit, 7 plus epsilon, 7 minus epsilon. So that's the way it works. All right. Continuity. A function has a limit at a. If the limit of f of x as x approaches a from the left, this notation, a from the left, equals L, and it's equal to the limit of f of x as a approaches from the right. So a from the left, a from the right. If the left and right result in the same thing, then the limit of f of x as x approaches a equals L. Direct substitution property. For polynomials or rational functions, if the function exists at the value a, then the limit of the function as x approaches c is equal to the function's value at a. That means the limit of f of x as x approaches a equals f of a. This is the definition of a continuity. A function is continuous if the limit and functional values are the same. This is the limit of f of x as x approaches a. This is the functional value f of a. If the two are identical, a function is continuous. So a function is continuous from the right if the limit of f of x as x approaches a from the right equals f of a, and a function is continuous from the left if the limit of f of x as x approaches a from the left equals f of a. And now we're going to look at this graph and come up with IVT, the intermediate value theorem, which indicates if f of x is a continuous function, that's a key, on the closed interval of a to b, that's another key. So we go from a to b, it's a closed interval. And it's a continuous function, so there can't be any break or holes. And let n be any number between f of a is here, f of b is here, and n is some number in between, where the two values are not equal. F of a is just different than f of b. In this case, more specifically, f of a is less than f of b. There must exist a number c in the interval of a to b such that f of c equals n. In other words, if you have a continuous function that has two different functional values, it must cover every functional value in between because it's continuous, including n. More specifically, we look at the case one side is positive, one side is negative. Therefore, we look at 0 of a function, the root of a function, if you will. Determine C such that P of X is continuous at X equals 5. P of X is defined as a piecewise defined function, X squared minus 25 over X minus 5 when X is not equal to 5. It is C at precisely X equals 5, reminding you that CTS short for continuous. The limit of f of X as X approaches a must be equal to f of a. So we look at the limit. To take a look at the limit, we have to use the top piece because the top piece exists everywhere when X is not equal to that. So let's take a limit of the function as X approaches 5. If we plug in 5, by the way, class, we get 0 over 0, which is indeterminate, and the technique is factoring. As you know, this is x squared minus 5 squared, or a squared minus b squared, which is a minus b times a plus b. So the numerator is x minus 5, x plus 5. Also, because x is approaching 5, you're hoping that you have a factor of x minus 5 to cancel it out, and you do. So you get limit of x plus 5 as x approaches 5. Now you plug in, you get 10. So the limit exists and it's equal to 2, equals to 10. The functional value exists and it's equal to c. If you want it to be continuous at x equals 5, the two must be identical. Therefore, the limit of p of x as x approaches 5 must be equal to p of 5 must be equal to c. C must be 10. F of x is sine x. If x is less than or equal to pi over 4, cosine x if x is larger than or equal to pi over 4. And we need to recognize each piece, it's a piecewise defined function, as a trigonometric function. And sine and cosine both have domains from negative to positive infinity. So each piece is continuous entirely from negative infinity to infinity. Therefore, this is continuous from negative infinity to pi over 4. This is continuous from pi over 4 to infinity. The only thing we need to check is the endpoint, namely pi over 4. So according to this, therefore, we do know that f of x is continuous on the interval of minus infinity to pi over 4, union pi over 4 to infinity. We don't know at pi over 4. That's why we are not using brackets yet. When we are sure, then we can use bracket. So let's check. What are we checking? Let's check that it works at pi over 4. So basically, take the limit of the function, okay, as x approaches pi over 4 from the left, which uses the top piece. Because it says x is less than pi over 4, you have to use sine x. And plug in sine of pi over 4, we should know it's square root of 2 over 2. We do the same thing as x approaches pi over 4 from the right, which means we use the bottom piece cosine x. And now if we plug in, obviously cosine of pi over 4 is also square root of 2 over 2. Which means f of pi over 4 is cosine of pi over 4 equals square root of 2 over 2 as well, simply because the last part is look at the equality. That is the functional value. By any chance, if we don't have any equality, that means f of pi over 4 is missing. If we have equality, the one that has the equality, that's the function you use. F of pi over 4 is cosine of pi over 4 is square root of 2 over 2. Therefore, everything works. The limit of f of x as x approaches pi over 4 equals f of pi over 4 equals square root of 2 over 2, which makes it continuous at pi over 4. And if it is continuous at pi over 4, then this becomes negative to positive infinity. The function is therefore continuous on the entire interval of negative to positive infinity. Okay, types of discontinuities. Let's look at this function. Let's look at this function. F of x is x squared minus x minus 2 over x minus 2. This function is the same thing when x is not equal to 2 and at x equals 2 is equal to 1. This is the functional value. So this one doesn't even have a functional value, and there's a hole, and of course we have a discontinuity. So parts A and C are known as removable discontinuities. In short, we can fix them. We could remove the discontinuity by redefining f of x at just the single number 2. Now, I'm going to remind you, when we have a rational function, we have to exclude what makes the denominator 0. So if you simplify, in this case, x minus 2, x plus 2, and x minus 2 crossed out, and you get x plus 1, y equals x plus 1 is the line. And this function is the line with a hole at, because x can't be 2, at x equals 2. So if you plug in 2 into this, the coordinates of the hole becomes 2, 3. So again, so there is a hole. This one at x equals 2 is defined to be something else like 1. But nevertheless, both of them are discontinuous, and both of them can be fixed by redefining the functional value. If we redefine the functional value to be 3, it works out. So the function g of x equals x plus 1 is a continuous function. That means the line without a hole. Now, we have a different story here. F of x is 1 over x squared if x is not equal to 0, and 1 if x is 0, and absolute f of x is the greatest function value. So in these cases, there is no way to fix things. So this is the infinite discontinuity, also known as vertical asymptote. This one is a jump, and in both cases, there is no way to fix anything. So infinite discontinuity or vertical asymptote, jump, these two cases, removable discontinuities. All right, reminding you of the definitions, limit of f of x as x approaches is equal to f of a one-sided limit. And now for this question, at what point or points is f of x discontinuous? Name the discontinuity. If removable, how would you redefine to remove it? In other words, how do you fix it? All right, notice there is a, so we have a hole here, -2. We have a hole here, -0.5. We have a jump here, hole here, discontinuity 0, discontinuity at 1, discontinuity at 3, discontinuity at 5. So we have a bunch of them. Let's see what they are. Let's name it. So if you look at 0, this one there is a jump, and this one there is a jump. At 0 and 1, we have a jump, and there's nothing we can do to fix it. Number 3, infinite, also known as VA or vertical asymptote. The rest of them are fixable. So if you look at -2, everything is fine. They are connected except there is a hole there. So that's good. This one, -0.5, the same thing, 5, the same thing. So those 3 are considered removable. Again, there are still discontinuities there, but removable nonetheless. That means we can fix it. So how do we fix it? Let's start with -2. If you look at -2, so redefine. If you look at -2, as we approach -2 from the left and right, from the left we are moving this way, from the right we are moving this way, and this hole has the y coordinate 2. So the limit of f of x as x approaches -2 exists and is equal to 2. So if you choose f of -2 to be equal to 2, that fixes the problem. That's for the first one. The next one is -0.5 here. Again, notice from the left and right. So this is -0.5. Left and right, we are moving towards the same hole. And the limit of f of x as x approaches -0.5 is the y coordinate of this point, which seems to be 3.5. So if we say, and f of -0.5, by the way, is given as 1. So we redefine it such that f of -0.5 is 3.5. So again, this one doesn't have a functional value because there's no solid point. This one does, but it doesn't do us any good. It makes it still discontinuous. Finally, number 5, take a look from the left and right. Left, we go this way, right, we go this way. In both cases, we are moving towards the same point. And you look, the limit of f of x exists as x approaches 5 and it's equal to 5. So you define f of 5 as 5 to fix this removable discontinuity. So it can be fixed. Use the intermediate value theorem to show there is a root for this equation in the closed interval of 1 to 3. Sine x is x squared minus x. And reminding everybody about IVT, if f of x is a continuous function on the closed interval of a to b, and let n be any number between f of a and f of b, where the two values are not equal, there must exist number in AB such that f of c equals n. So to do so, we are going to bring everything to the same side, this one to this side, or this one to this side, and set it equal to 0 and give it a name, f of x, g of x, h of x, your choice. So bring everything to one side. It doesn't matter which way. For example, x squared minus x minus sine x equal to 0. They are equivalent. Call it the function f of x. So f of x equals x squared minus x minus x is a minus sine x is a continuous function because it's a combination of polynomial. This is a polynomial of degree 2 or squaring function or parabola. So this is a polynomial of degree 2 and this is a sinusoidal function. Each one has a domain which is already in numbers. None of them has a restriction. And therefore, it's continuous from negative to positive infinity. Okay. which makes it continuous in the interval of 1 to 3. So this is continuous in the interval of negative to positive infinity. All right, so let's look at a way to come up with f of 1 and f of 3, and it's done by inspection. So if I plug in one of the endpoints, it's less than 0. Why is that? Let's find out. Plug in 1. It becomes 1 squared minus 1. Both of them are 1, so they cancel each other, right? So you get negative sine 1. And please understand, sine 1 means sine of 1 radian at 57.3 degrees, and that's negative. You don't even have to know what the answer is, but it's negative. And that's the key. You just want the sign, negative or positive. We are going to do the same thing for number 3. Now, f of 3, we know it to be positive. How do we know that? Plug in. 9 minus 3, 6 minus sine 3. Notice sine, the largest value, the maximum value is 1. 6 minus 1 is still positive. So no matter what sine of 3 is, it doesn't matter. This value is positive, which makes 0 a number between f of 1 and f of 3. So if this has a root, has a 0 somewhere between 1 and 3, as we proved it, in other words, IVT applies because the function was continuous and it was a closed interval. So f of x is continuous on the closed interval of 1, 2, 3, and has a root in between. So again, the way the IVT is used, you normally deal with it in a manner that you make some value negative, one positive, and it goes through 0. Limits of functions at infinity. Here's the summary definition: horizontal asymptote HA of the curve y equals f of x as the equation y equals L. If the limit of f of x as x approaches negative infinity is L, or the limit of f of x as x approaches infinity is L. The limit of 1 over x as x approaches infinity is 0. The limit of 1 over x to the power of p as x approaches infinity is 0, as long as p is positive. For example, this one, a function, is a function you probably remember from pre-calculus. And so because this is 0, that means y equals 0, which is the x-axis, is the horizontal asymptote. Now, exponential functions, y equals b to the power of x, where the base is larger than 1, are exponential growth, in which case, if the base is between 0 and 1, makes it a exponential decay. Now, the end behavior, the limit of e to the power of x as x approaches minus infinity is 0. It's going this way. And that is really the definition of horizontal asymptote, the x-axis y equal to 0. This one, the limit of f of x as x approaches infinity is infinity. That end behavior that was taught in algebra, that refers to the first quadrant. Whereas this one, the limit of f of x as x approaches negative infinity is infinity. And that refers to the second quadrant. The limit, as an example, of e to the power minus x. E to the power minus x is an example of an exponential decay. limit of e to the power minus x as x approaches infinity is 0. And as I mentioned, this means the horizontal asymptote has the equation of y equals 0. Y equals x cubed. It's one of those essential functions we should know the graph. And so obviously, the limit of f of x as x approaches negative infinity is negative infinity, refers to the third quadrant. Limit of f of x as x approaches infinity is infinity, refers to the first quadrant. And that is known as the end behavior of the function, everybody. This is what we have already learned. What about VA, vertical asymptote? What is the definition of that in calculus? Limit of f of x as x approaches a, or a from the left, or a from the right. If it's either negative or positive infinity, then the vertical asymptote VA for short has the equation x equals a. For example, we are familiar with the logarithmic functions like natural log. As you know, the domain is all real numbers. The range is from negative to positive infinity. The x-intercept at 1, 0. There is no y-intercept. And you can see the vertical asymptote, the limit of ln x as x approaches 0 from the right is negative infinity, which means the y-axis, x equals 0, is the vertical asymptote. So what is the definition of a vertical asymptote? Again, vertical asymptotes, VA of the curve y equals f of x is x equals a if the limit of f of x as x approaches a is positive or negative infinity, or limit of f of x as x approaches a from the left or right is positive or negative infinity. You're all familiar with the tangent function. It's got, for one complete cycle, it's got two vertical asymptotes, x equals negative pi over 2 and x equals pi over 2. The limit of tan x as x approaches negative pi over 2 from the left is negative infinity. We're talking about this one. So that means VA x equals minus pi over 2. On the other hand, if you look at this one, the limit of tan x as x approaches pi over 2, it's equal to infinity, and that makes it the VA x equals pi over 2. This is pi over 2 from the left, everybody. The left side of pi over 2. This is from the right. All right. Of course, remember that it's a periodic function. It's continuous indefinitely, so it has infinitely many vertical asymptotes. This is just one complete cycle going from minus pi over 2 to pi over 2. And its inverse. The limit of tan inverse of x as x approaches negative infinity is minus pi over 2. The limit of tan inverse as x approaches infinity is pi over 2. And therefore, we have horizontal asymptotes. This one and this one are inverse functions. Vertical asymptotes become horizontal asymptotes. Y equals pi over 2 is this line, and y equals negative pi over 2 is this line. All right, I want to find the limits, and I'm going to remind everybody to find the limits, just plug in and observe. If the limit of f of x as x approaches a is equal to a number, you're done. If that is 0 over a number, it's 0 and you're done. If it's a number over 0, it's infinity or negative infinity. And you have to figure out which one. We'll go over that. And most of the time, we come up with the indeterminate forms of 0 over 0, infinity over infinity, infinity minus infinity, and so on. So that's important to understand. Okay. All right. So if you look at this one, if you plug in t is approaching infinity, you get infinity over infinity. So what is the technique? The technique is very simple, everybody. Because t is approaching infinity, you divide by highest degree term in the denominator, namely x squared. That's the methodology. And you simplify each one. Because t is a because t is approaching infinity, this one, this one, this one, all of them go to zero except one. It's important the answer is 0 over 1, which makes it 0. And I want to emphasize the denominator is not 0. I can't emphasize this enough, okay? Let's look at the next one. In the same manner, we notice if we plug in, we get infinity over infinity, and the technique is the same because this is a rational function. T is approaching infinity. We divide by highest degree term in the denominator, namely t. And we're going to simplify. We're going to plug in. So this is infinity, this is 2, this 0, 5, 0. And so infinity plus 2 or plus 2 billion makes no difference, is infinity, and divided by 5 or any large number makes no difference, is infinity. The only thing is if it's negative, becomes negative infinity. If you plug in, you get infinity squared plus 1, which is infinity squared of that is infinity, so you get infinity minus infinity. So the technique is to, when you have a square root, is to multiply and divide by the conjugate. As you recall, the conjugate of a minus b is a plus b, therefore the product is a squared minus b squared. So you're going to multiply by the same thing plus x and divide by x. Remember, this expression is 1, so that's okay. So when you multiply, the denominator remains as square root of x squared plus 1 plus x. The numerator becomes, here's the numerator, a squared minus b squared. So square root of x squared plus 1 quantity squared comes out, and these two cancel each other. And now if you plug in infinity, you do get infinity here, and the answer is 0. Again, indeterminate form, anything can happen. The limit of 12 over 4 plus 3 to the power minus t as t approaches infinity, if you plug in, you get 0. Why is that? A to the power of minus m is 1 over a to the power of m. This is a negative exponential rule. Therefore, e to the power of minus t is 1 over e to the power of t. And so if you look at this one, it's 1 over e to the power of infinity, which is 1 over infinity, which is 0. So the answer is 12 over 4 or 3. What about this one? This is not a rational expression. It's a fractional expression because e to the power of t is a transcendental function. But the technique is the same because t is approaching infinity. You divide by highest value in the denominator, which is e to the power of t. So divide everything by e to the power of t because when you plug in, you get infinity over negative infinity. By the way, the bottom, because of this negative 3 in front of e to the power of t, becomes negative infinity. So divide by e to the power of t. and simplify. E to the power of t, because t goes to infinity, that is 0, that is 0. Positive 1 over negative 3 is the final answer, or negative 1/3. What about this one? Just plug in. Infinity squared is infinity, minus infinity. It's an indeterminate technique. Factoring. We are going to factor the x out. And now it's infinity times infinity minus 1, which is infinity. Limit of x squared plus x over 3 minus x as x approaches infinity. This is a rational expression. Because x is approaching infinity, you divide by highest degree term in the denominator, namely x, and simplify. So as you divide everything by x, you get x plus 1 over 3 over x minus 1. And we're going to replace the x with infinity. This becomes infinity plus 1. 3 over infinity becomes 0. And infinity plus 1 is infinity over negative 1. The only thing you want to be careful of, because of the sign in the denominator, we get negative infinity. Limit of e to the power minus x plus 2 cosine 3x as x approaches infinity. We are going to separate them using the limit laws. This one becomes 0 because it's e to the power of minus infinity, okay, or 1 over e to the power of infinity. But what is the second piece? It does not exist. Therefore, the result does not exist. Why is that? The problem is cosine. In general, the limit of cosine, doesn't matter what the argument is, ax as x approaches infinity does not exist. Same thing for the sine, because they oscillate between negative 1 and 1. As you know, the range for sinusoidal functions is negative 1 to 1. What about this one? I hope you realize that if you plug in, you get e to the power of infinity minus 0, e to the power of infinity minus 0, which is infinity over infinity. And again, this is not a rational expression, but the technique is the same thing. Because x is approaching infinity, you divide by highest value in the denominator and you simplify. So I hope you can see that if I divide these two by e to the power of x, I get 1, and these two I get e to the power of minus 6x. Because a to the power of minus m is 1 over a to the power of m, of course, here. And this one, a to the power of m over a to the power of n, is a to the power of m minus n. So if you divide this one by this one, so e to the power of minus 3x, you divide by e to the power of 3x, it's e to the power of 3x minus 3x minus 3x, which is e to the power of minus 6x. And as you know, both of them go to 0 because x is approaching infinity. E to the power of minus 6x, again, the negative exponential rule. And this goes to 0, this goes to 0. The answer is 1 over 1, or simply 1. Again, this following the negative exponential. What is the limit of tan inverse of ln x as x approaches 0 from the root? We're going to use the limit laws, and we are going to bring the tan inverse out because the limit pertains to x. So you're interested in tan inverse of this piece. So we're going to concentrate on that piece. What is the limit of ln x as x approaches 0 from the right? I showed you previously. If you look at the graph of y equals ln x, that means limit of ln x as x approaches 0 from the right. That means this is negative infinity. That's the meaning of it from the graph, negative infinity. So you want Tan inverse of negative infinity, some of you already know the answer is minus pi over 2 from trigonometry. Or just to remind you, when we look at a tangent graph, we have two vertical asymptotes for a complete cycle. Okay, otherwise we have infinitely many. X equals minus pi over 2, x equals positive pi over 2, and its inverse has to have two horizontal asymptotes, y equals pi over 2, y equals minus pi over 2, and the answer is minus pi over 2, tan inverse of negative infinity. So as we go towards negative infinity, it goes towards the horizontal asymptote of minus pi over 2. What about this limit, the limit of sine squared over x squared plus 1 as x approaches infinity? We've looked at a similar question. Anytime sinusoidal functions are involved, the technique is to use the fact that in the case of a squeeze theorem, if g of x is between f and h, when x is near ax, possibly at a, the limit of f of x and limit of h of x as x approaches a, both of them give us L, then the middle one, the middle function, the limit of g of x as x approaches a is the same thing. And the technique is remembering the range for sinusoidal functions is -1 to 1. So if sine is between -1 and 1, then you try to get to this expression. So if you square that, remember what happens. You square that, this one you square, but this is 0 because even right here is between 0 and 1. This is between 0 and -1. Still you get 0, but you can't say I'm going to square this and I get 1. That's extremely important to know. You wanted to make sure it looks like that. And x is approaching infinity, x squared plus 1 is positive, multiplied by 1 over x squared plus 1. This is also a positive expression. Therefore, the inequality does not flip over. So multiply both sides by this. 0 doesn't change. The right side becomes 1 over x squared plus 1. And the middle term is exactly what we are looking for. So this one, the limit of 0 as x approaches infinity is 0. This one, the limit of 1 over x squared plus 1 as x approaches infinity obviously is 1 over infinity or 0. And by the squeeze theorem, we say the limit of the expression sine squared over x squared plus 1 as x approaches infinity is 0 by squeeze theorem. Find asymptotes. F of x is 2x squared plus 1 over 3x squared plus 2x minus 1. To find horizontal asymptotes, we take a limit as x approaches infinity or negative infinity. So take the limit of this expression where x approaches positive or negative infinity makes no difference. The technique is the same. You have to divide by highest degree term in the denominator because it's a rational expression. And we are going to divide the top and the bottom by x squared, term by term, simplify each. Whether you approach infinity or negative infinity makes no difference, everybody. This piece goes to 0, this piece and this piece goes to 0. The answer is 2/3. Therefore, horizontal asymptote has the equation y equals 2/3. And you probably remember from pre-calculus, when you have a functional value like that, where the degree of the numerator and the denominator are the same, the answer is 2/3, y equals 2/3. In other words, the leading term will take over. The vertical asymptote has a definition. And what it means, the limit of f of x as x approaches is positive or negative infinity. How do you get there? If the denominator is 0, you set the denominator equal to 0, and you solve that. So this is a prime number. Three and 1, so you have to pick numbers here because this is -1. You have no choice but to go with 1 and -1. You just want to make sure that the middle terms add up to 2x. They do. So x equals 1/3, x equals -1. Those are the vertical asymptotes. We want to find a formula for a function that has vertical asymptote x equals 1, x equals 3, horizontal asymptote y equals 1. It's important to understand this is a possibility. Okay, so, well, one possibility is, if you look at x equals 1, that means we need a factor of x minus 1 in the denominator. If you look at x equals 3, that means we need the x minus 3 factor in the denominator. Now, if you look at the denominator only for now, you recognize this as x squared, and doesn't matter what happens next. With the leading term is x squared. So if you want y to be 1, the numerator has to have the same degree, x squared, and with the same leading coefficient. This is one possibility. If I add x, still the same. If I add 1, it's still the same. So I can make a lot of changes, but this is one possible solution, everybody.